This is our programmable square wave generator implemented on the Nexys A7 FPGA board. For the basic I/O configurations, we have the first four switches from J15 to R15 right here. Those switches indicate our input data M, which is the user-specified amount of time in which the output waveform will be high. And from R17 to R13, those next four switches indicate the input data N, which is the user-specified amount of time for the clock pulse in which the output will be 0. Over here, the final switch is V10. In the far left corner, this is the synchronous reset, which will go into effect at the clock pulse, at the positive edge of the clock pulse for the onboard oscillator of the FPGA board. For the outputs, we are using only the JA header. And the JA header, we're using pin number 1 to be the output signal, so the logic high and logic low of the waveform. And this is connected to an input channel on an oscilloscope. And pin number 5 of the JA header is connected to ground, which is thus also connected to the oscilloscope. So before I go into the demonstration, I'll cover a little bit about my oscilloscope settings. Right now, I have the oscilloscope settings with the x-axis for the time being represented by 100 nanosecond divisions. So each division is 100 nanoseconds, and I have the waveform shifted down just a bit so it's a better display on the screen, so that it can be more visible for the demonstration. So it still is reading a proper peak-to-peak value. It looks like about 3.45, somewhere around 3.5 volts. It's just that the output waveform is shifted down a bit just for the demonstration purposes. So it's still representing logic highs and logic lows. I just have it shifted to be a little bit more visible. Also, my oscilloscope isn't the best, it doesn't have the fastest sampling rate, so when the period is extremely low, like in this situation, a period of 200 nanoseconds, it looks like there's a lot of noise and it looks as if it's caps charging and discharging. When I increase the period to a much larger value, you will see a more well-defined square wave with more well-defined discontinuities at the pulse edges. So right now I have M equals 1 and N equals 1. So right now each division is high for 100 nanoseconds and low for 100 nanoseconds, giving a period of 200 nanoseconds as expected. Right now I will also demonstrate the synchronous reset. I will hit the reset, and at the positive edge of the clock pulse on the onboard oscillator, this will go to 0. And there we go. So that was the synchronous reset feature. Right now I'm going to come back to the FPGA board, and I will increase M to be 2, and I will keep N 1. So we would expect the wave pulse to be high for 200 nanoseconds and low for 100 nanoseconds, which is what we get. It's a little bit more well-defined now as we increase the period on my oscilloscope sampling, but the period is 300 nanoseconds, and based on the divisions, it's high for 200 nanoseconds and low for 100 nanoseconds. I'm going to now increase it from having N as 1 to now N is equal to 2. And so now, coming back, we should be expecting 400 nanosecond period, which we see in the bottom corner, and it is high for 200 nanoseconds and low for 200 nanoseconds. It keep changing the configurations. It could go 3 and 1, for example. So M is 3 and N is 1. We should still be expecting the 400 nanoseconds, which we do. But now the output signal is high for 300 nanoseconds and low for 100 nanoseconds. So once again, the sampling is difficult for my oscilloscope as it's not a very high-end oscilloscope, but it still is providing this somewhat quasi-square wave. So now what I will show is that if I increase the period, for example, if I throw M equals 15 and N equals 15, right now it's out of range. So if I hit auto for auto scaling, now it's going to generate this beautiful square wave with the discontinuities present. And so since M is 1500 nanoseconds and N is 1500 nanoseconds, we would expect a period of 3000 nanoseconds, which is 3 microseconds, which is shown in the bottom left corner region. And each division now is 1 microsecond. So we have the square wave pulse is high for 1.5 microseconds and low for 1.5 microseconds, which is the nature of what was input into the FPGA board. So that is essentially the functionality, and it's working properly. The only constraint here is the oscilloscope, but still was able to provide for the demonstration. And that's it. Thank you.